Hello everyone, welcome to the second lecture on computer architecture and organization. In the last lecture, we discussed about the computer as the product of the vibrant information technology industry, and we saw some applications of this computer era, which we named as computer science fiction. The computer science fiction's what our textbook says is that what is the fiction today may turn into the killer applications tomorrow. So we saw some examples for this computer science fiction as well as the killer applications. And the next thing we discussed about the classes of computing applications. So what are all the classes of computing applications? There are three main classes of computing application. First is the personal computers, which we are extensively using nowadays, and the second thing is servers. Servers are nothing but the large computers which look like our personal PC, but it consists of many or hundreds of processors inside to do a single complex application or many small jobs. Supercomputers comes under the category of servers. And the third thing which we discussed is embedded computing application. The very important point in this embedded computing application is that it demands a very minimum requirement, that is it concentrates only on the performance. As an example, we saw about this music processors and digital home appliances, what's the demand in this home application is that they need to perform a single application perfectly or single function perfectly. And next, under the category of this embedded computing applications, we discussed about this personal mobile devices which we are using nowadays, and we discussed about this touch screen. And later we saw about a giant data center, that is cloud computing, and the giant data centers are called as the warehouse scale computers. So far we have discussed in the previous lecture, and in this lecture, we are going to see about the aim or the motive of this course. So, at the end of this course, we must able to answer the following questions that is prescribed by your textbook. So, before that, we must know what is the performance of the program. So, once upon a time, or in the early 1960s and later 1970s, the programmers thought that the programs will work perfectly if they get the result very quickly. So, the performance depends on how fast they are getting the result outside of the program as a result of the program. So the programmers often followed a simple credo: minimize the memory space to make the programs fast. So 1960s and 1970s, a primary constraint on computer performance was the size of the computer's memory. So only they followed the simple credo, that is to minimize the memory space to make the programs fast. But nowadays, or in the last decade, these advances in this computer design and memory technology have greatly reduced the importance of the small memory size in most applications other than those in embedded computing systems, because in embedded computing systems obviously the memory space will be very less. So apart from this embedded computing applications, we need to enhance the memory as well as we need to enhance the performance of the program. So the programmers interested in performance now need to understand the issues that have replaced the simple memory model of the 1960s. So 1960s they followed a very simple model, but today the memory space is little bit modified by two important concepts. One is the parallel nature of the processes, and the next thing is the hierarchical nature of memories. So also the today's programmers need to worry about the energy efficiency of their programs, that is either it may be run on the personal mobile devices or cloud computing. So the programmers cannot design of their own. They should know what is below the program that is running, or what is the code that is running behind the program. Also they must know about the architecture that lies under the covers of a computer system. So, at the end of the course, you will be able to answer the following questions. The first is that you must understand the aspects, concepts regarding the aspects of both the hardware and the software that affect the program performance. Say, for example, we are writing a program, a high level language like C or Java. So, that C or Java should be converted into the language of the hardware, and the hardware should execute the program. So if you are writing a program, then we must know very clearly about both the hardware as well as the software. And the second thing is that we must know the interface between the hardware and software, because if you are writing a program in a language, that program should instruct the hardware to perform the function correctly. So you should know the logic correctly so that you can frame the program, then the program will be converted into the instructions that are executed by the hardware. So second point, if you see the second point, what is the interface between the hardware and the software, and how does software instruct the hardware to perform the needed functions. So these concepts are vital to understanding how to write many kinds of software. And the third thing is that we need to analyze the performance of the program. If we speak about the performance of the program, as we have discussed in the first 2 points, it depends on the first 2 points. So the first thing is that it depends on the original program, and the second it depends on original program, the software translation of that program into the computer's language, and the third thing, it depends on the effectiveness of the hardware that executes the program. And the fourth is that what techniques can be used by hardware designers to improve the performance. So the hardware designer may use several techniques to improve the performance, but he should be very confined to a particular technique. So he should know which technique may develop the performance of a program or performance of an application. Coming to this point, we should know the hardware designers must know how to improve the energy efficiency. Energy efficiency also decides the computer program's performance. So we must know how to have a good percentage of energy efficiency. Either it may be whether it may be in the personal mobile devices or in the cloud computing systems. So both the hardware and software must be good in order to improve the energy efficiency. And the next thing is that since the first commercial computer in 1951, what great ideas did computer architects come up with that lay the foundation of modern computing. So through the empirical process or through the experience too, the designers must be able to design the program or design the architecture of a hardware. Okay. So without understanding the answer to these questions, improving the performance of your program on a modern computer or evaluating what features might make one computer better than the another for a particular application will be a complex process of trial and error rather than a scientific procedure driven by, that is, insight and analysis. Okay. Speaking about the performance of a program, it depends on three factors. The first thing is the effectiveness of the algorithm used in the program, and the second one is the software system, and the third one is execution of instructions by computer. So if you see here the performance of the program, if you are writing a program for swapping the numbers or in order to perform the matrix additions, it depends on the three factors. The first is algorithm, and the second one is that the programming language, compiler or architecture, and the third thing is that the execution of instructions by computer. So if you see this, what is algorithm? Algorithm in the sense what we are writing the logic or function in our own language, or it may be in the high level language. So how it performs? Algorithm also affects the performance of the program or an application. So what is algorithm? How many lines we are writing the algorithm? So it determines both the number of the source level statement, what are all the statements we are writing, as well as the number of IO operations executed. So the logic may include more number of datas to perform the input and output operations. So this algorithm affects the performance by the two factors. One is the number of source level statements that we are writing in the algorithm, and the number of IO operations that are being executed by this algorithm. And the second thing is that the software system is the compiler or architecture that lies inside our design. So it determines the number of computer instructions for each source level statement. So compiler and architecture that converts, we all know that the compiler converts the high level language into the machine level language. So while converting that, it converts the high level language into the instructions that is understood by the computer. So it also affects the performance of the program. And the third thing is that processor and memory system, it is under the hardware part. So the hardware also has an impact on this program performance by how fast it can execute the instruction and how fast it can produce the result for a program. So processor, memory, IO system, they are all hardware systems. So this hardware part, the software part, as well as the code that is written by the human strength, everything determines the performance of the program. Now we are going to discuss about the 8 great ideas in computer architecture. So these are all the great ideas that is followed by the designers or the computer architects who designed the first computer. So nowadays too, the modern computer architects also follow the same great ideas or imitate the great ideas that have been used for the first computer system or the processor. Among this, the first great idea is Moore's law. So this law is given by Gordon Moore, one of the founders of Intel. So when a designer starts to design a project, he should keep in mind, if say for example, if a designer designs start his design by this year, that is 2020, and if the design gets completed by 2025, he should know how many resources can a chip can hold in 2025. So according to that, he should know the design, he should plan his design. So that is the law. That is given by Moore. So whenever a computer architect or designer design a system, he should keep in mind how the design will be in 2025, and the design should cope up with all the specifications at that time. So what this Moore's law states is that the integrated circuit resources double every 18 to 24 months. So he predicted that in 1965 itself. So the resources available per chip can easily double or quadruple between the start and finish of the project. So this point should be in the minds of the computer architects and designers, and this is denoted by the icon up and to the right Moore's law graph. So whenever in the course, if there is if the architect is planning for the future design, then this icon will be represented. The second great idea is the use of abstractions. What is the need of this abstraction in the sense? Both the computer architects and programmers had to invent the techniques to make themselves more productive. So one of the major productivity technique for hardware and software is to use the abstractions. So what this abstraction does is that it is used to represent the design at different levels of representation. So the lower level details are hidden to offer a simpler model at higher levels. So here we are using the abstract painting icon to represent this second great idea. And the third great idea is making the common case fast. So what is this common case? Say for example, take the hardware technology is the same for 3 or more designs. The designs may be several, but the hardware technology is the same for all the designs. Depending upon the design and the application, the hardware technologies are employed in different ways. So the hardware technology is the common case here. So we should identify which is the common case. So the common case, we can make this common case very fast. We can design the common case very fast once we design an application. So once the common case is designed, then we can go for the rare case. Rare case in the sense we should optimize the power or we should optimize the energy according to the applications. So this is a common sense. So from the common sense, we can identify which is the common technology or which is the common case that employs in all the designs. So enhancing the common case performance is better than optimizing the rare case. What it means is that we should enhance the common case fast, then we should optimize the rare case. So here it is denoted by a sports car icon. We use a sports car as the icon for making this common case fast, as the most common trip has 1 or 2 passengers, and it's surely easier to make a sports car than a fast minivan. Okay. And the fourth great idea is performance via parallelism. So since the dawn of computing, computer architects have offered designs that get more performance by performing the operations in parallel. So here the icon is, we have used this multiple jet engines of a plane as an icon because of this parallel performance. Okay. So in the upcoming lecture, we will see the remaining great ideas. Thank you.